Good evening, everyone. Good morning, good day. The voice that you are hearing is the voice of Mr. Msomi, who specializes in teaching natural sciences, physical sciences, and also technical sciences. So, looking at this video, we'll be focusing only on Newton's second law, where it is our question 2 on our paper 1 question paper in physical sciences and also in technical sciences grade 12. But this is not limited to only grade 12, even grade 11. If you are there on you're struggling with Newton's laws, you are struggling with calculating Fnet, calculating acceleration and so not. This is your platform as well. So where are we going to start? So before we start anything, you should understand that there are possible definition that they may ask in the exam based on question 2 on Newton's laws. So first of all, it is Newton's first law. Secondly, Newton's first law goes hand in hand with inertia, and then after that you are going to have your Newton's second law, for which this video is only based on Newton's second law calculations. And then you're gonna have your Newton's third law. You have to know your Newton's third law. Also, you are going to have to know kinetic frictional force, static frictional force, and normal force. Those definitions, you should know them by your heart. So let us start with Newton's second law. So if you are looking at Newton's second law, so as we are looking at Newton's second law of motion, so first of all, you remember that we are using the formula F net is equal to ma. So this is ma. So what they normally tell you there in that particular definition on that particular law, they say when a resultant force acts on an object, a resultant force is our F net, acts on an object, the object will accelerate in the direction of the force with an acceleration that is directly proportional to the force and inversely proportional to the mass of an object. So what does that mean? It simply means here, simply because they are simply focusing on acceleration, the proportionality of acceleration with mass and the proportionality of acceleration with net force. So it simply means we are supposed to make A the subject of the formula in this case. So it simply means we are going to divide by m on that side, and then we divide by m on the other side. Then m divided by m is going to give you 1, and then 1 multiplied by a, you are simply left with a on this side. So we can make this a on the other side, because this equal sign means whatever is on this side is equal to whatever is on the other side. So if you swap them, it's still the same thing. So we are having a is equal to f net divided by m. So now one thing that you have to make sure that you understand is that this a, for you to have that definition in your head, you should have this a as a fraction. So a is simply a over 1, and then f net is divided by m on the other side. So what does this mean? This simply means acceleration and your net force, which is F net, resultant force. As both of them, they are numerators in this case. So when both of them are numerators in this case, that simply means they occupy the same position in different fractions. So since they are both numerators, that means they are directly proportional to each other. And then if we are looking at A compared with the mass, A in this fraction is your numerator, whereas m, it is your denominator. So it means these two, they are not occupying the same position in their different or perspective fractions. So this simply means they are inversely proportional. So that is why they say there in the definition of Newton's second law, the acceleration is inversely proportional to the mass of an object, but it is directly proportional to the force of an object, right? So without wasting our time, I believe this is going to be the next part. We are going to move on to the next part with our calculations. Right, so moving on with our calculations now, we're gonna start our real calculations. So now let us say normally I will just call them scenarios then. So let us say we are having the normal scenario. So the normal scenario, it is where we are having an applied force horizontal applied horizontally in an object. So let us say we are having a 5 kg block. So this 5 kg block, and we apply a force of 80 newtons horizontally. So it means there are no components in this case, in this applied force. So this is why I call it the normal scenario. So let us say the motion of an object is moving to the right. The motion of an object is moving to the right, and then let's say this is a rough surface. So when there is a rough surface, obviously there's going to be a friction. So when there is friction, we're going to assume that our coefficient of kinetic friction is 0.17. So this tells us that the friction is going to be in the opposite direction of motion, right? So first question, let us say they say draw a free body diagram. Draw a free body diagram of the above diagram of the above block. So normally the free body, we normally represent it with just a dot. So with the obvious forces, we are having these two forces. The force applied is going to the right, is applied horizontally, and then we are having Fk, which is kinetic frictional force. And then remember, why do we call it kinetic frictional force? We call it kinetic simply because the object, we are told that it is moving to the right. So if you want to be on the safe side, you can simply use FF. So this FF is not so specific to say this object, this kinetic or this friction is for an object which is moving or it's standing stationary. So, right? So, so for you to be on the safe side, you must label this as FF, right? Because it may happen that the object is not moving, and then when I use that FK, which is going to be wrong in that case. And then going down, we are having our FG, which is the weight, and then going up, we are having our normal force. So there are four forces acting in here. So that's most of the cases they're gonna give it 4 marks, right? So now let's go to question number 2. So in question number 2, they're gonna say maybe calculate the frictional force, which is our Fk, kinetic frictional force. We know the formula that is there on your formula sheets is Fk is equal to kinetic coefficient times the normal force. So in this case, what we need to understand is that the object is not moving vertically, but it only moves forward or is moving to the right, which is horizontal. So it means these two forces which are acting vertically, the F net or the net force of it is supposed to be 0 because the object isn't moving vertically, but it only moves horizontally. So let us say F net for the horizontal forces or for a vertical forces is equal to 0. Then now, what comprises of this F net for vertical forces? It comprises of the normal force and also the gravitational force, right? So we're gonna take the force which is going up as positive, so this simply means the force going down is going to be negative. Why are we doing this, all of this? It's simply because in our formula we are having a normal force. Normal force, we should understand what is the formula of the normal force according to these forces which are acting vertical. So our F net is going to be for vertical forces, the normal, which is positive. We always start with a positive force, minus Fg, minus our Fg, which is equal to 0 then, right? And then we shall make our n the subjects of the formula. It simply means we're going to transpose this negative Fg. So when we transpose this negative Fg, this negative Fg, when it goes to the other side, it's going to be positive Fg. And then we know for a fact that Fg is equal to m times g. So it simply means we can say n is equal to m times g. So that is why when we come back in this formula of kinetic friction, we are going to say Fk is equal to mu k, and then open brackets, because there are two quantities which are multiplying here, multiplying the coefficient. So it's going to be mass multiplied by the gravitational acceleration, right? So now I hope that is understood. We can just simply erase this part and do our calculations. So as we are doing our calculations, this simply means our Fk is equal to 0.17 open brackets. So let's just put this in brackets as well. 5 multiplied by 9.8 close brackets. And then if we punch our calculator, I believe we are getting 8.33 newtons. And then remember, frictional force, it is a vector quantity, so we shall put a direction just in case. So this friction, as we are looking in here, it is moving to the left, so we can simply say left, or you can simply say in the opposite direction of motion. It is still correct. Then our next question now, next question will be to say, now this is number 3. Calculate the acceleration. Calculate the acceleration of this object. So calculating the acceleration, in this case, now we are focusing only on the horizontal forces, because this object is accelerating horizontally, it is not accelerating vertically. So how do we deal with that? We are looking at the forces which are acting horizontally. We find that there are two of them, so we can simply say our F net is equal to ma. Then F net is comprises of F applied and Fk. Remember, F applied is going to be positive because the motion of an object, we always take that direction as positive, so it means the opposite direction is going to be negative. So F applied is going to be positive, we're going to have F applied minus our Fk, which is the kinetic frictional force, is equal to ma. And then the next part, we are supposed to substitute. Then 30 is our F applied minus 8,33, which is our friction. 8,33 is equal to 5, which is the mass of an object, times your acceleration. All right, and then solving for this 30 minus 8,33, I believe we shall find 21,67 is equal to 5a. So simply because now we are having 5a, let me just quickly take my calculator here. So taking a calculator, it simply means we have to solve for a now. So solving for a, we just have to look here. What is 5 doing in this a? 5 is multiplying a. So as for us, we want to do the opposite. It's like we are unpacking the box. So when you are packing a box, you put in a sellotape there, and then you pack it safe. And then if you are unpacking, you have to remove that sellotape. So we are going to apply the same technique here. We are looking for this a, so we want to remove whatever is next to a, so that a is standing alone. So what are we going to do there? We know that m is multiplying a, so it means 5 is multiplying this a. We are going to do the opposite. So what's the opposite of multiplication? Multiplication opposite is going to be a division. So we divide by 5 in both cases. So in that case, we're gonna have 21,67 divide by 5. So on this side, we are having 4,33 is equal to 5 divided by 5 is gonna give us 1. 1 multiplied by a, we are having a. So these two, they are simply just cancelling themselves out. So to put it in a proper manner, we're going to say a is equal to 4,33. Acceleration is in meters per second squared. In which direction? Our answer is positive. So which direction did we take as positive? It is forward, or you can say this is going to the right. So this is the main or the simplest scenario that we are going to have, right? So having this simplest scenario, I'm sure you have grasped the basics of F-nets and calculating the friction, and then how do we find the normal force, right? So right now, let us move on to the next questions. So moving on to the next questions or the next scenarios, let us start by explaining the coefficient of kinetic friction, right? The coefficient of friction, or you can say kinetic friction or static friction. Why it doesn't have the units? So remember, the formula of kinetic is equal to kinetic friction is equal to the coefficient of kinetic times the normal force, right? And then if we were to make the coefficient the subject, we're going to divide by n on both cases. Divide by n, which is the normal force. Then we know normal divide by normal. This simply gives us 1 multiplied by a coefficient. It means we are having a coefficient of kinetic is equal to the Fk divided by the normal force. So someone may be asking, where is this leading us to? Let us take the units of friction. So friction is given the units of newtons because it is a force, and also the normal it is still a force. It's given the units of newtons. So this simply means newtons over newtons is just giving you one. The units, SI units, they are going to cancel themselves out. So that is why when you look at this particular coefficient, it does not have any units. I'm sure these questions they normally ask there by the end of question 2. So if ever they ask you why is the coefficient of kinetic friction is not having the units, so you are able to answer by saying it is a ratio of two forces. Therefore, the units, the SI units of the two forces cancel themselves out. Right? All right. So let us move on to our second problem. So in our second problem now, we are focusing on F applied. Let's say F applied at an angle. So at an angle. So if we're having F applied at an angle, now it's going to be a different scenario now. How? Let us start with the, let's call it the second scenario now. So let's call it the second scenario, which is going to be scenario, which is going to be, let's say F applied is diagonally up. Is applied, this force is applied diagonally up, right? So let us have a diagram to show that. So a diagram, let's still continue with a 5 kg block, so that when you have a difference, to see what effects does it have on the friction, what effects does it have on the normal force. So we're having a 5 kg, and then now they apply the very same force, which is F, which was at 30 newtons, but now they apply it at an angle of 30 degrees, right? And then everything remains the way it was. So the coefficient is still 0.17, and then so it simply means this frictional force, kinetic frictional force in this case, right? So what will be different now? First of all, let us look at the free body diagram. So let us look at the free body diagram. So free body diagram, you may notice always we are using a dot to represent the body there if it's free body, and then we still have F applied, but now this F applied, it is at an angle. We still have our frictional force, which is kinetic frictional force, because the object is moving. Forgot to mention there, what's the motion of an object. Motion of an object is still going right. And then now we are having the force. We still have the force going down, which is our weight or gravitational force. And then going up, we still have our normal force, right? Now the next part is that we have to have an understanding of what comprises of this force applied at an angle there. So here's our force applied at an angle. This is our force applied, right? And then for us to have a clear understanding of where is your x component is supposed to go, because now if it's applied at an angle, that simply means there is an x component and there is a y component. So the x component, just remember, if ever you are drawing this type, you are drawing a triangle, sort of a triangle, For components, it must follow a head to tail method, but for the force applied, it must follow a tail to tail and head to head. So this simply means in the tail of this F applied, I should be having the tail of my X component. So this is Fx. So it's a tail to tail for this F applied, right? And then, so it means here I should be having the head because it must be a head to head method. But for the components, it must be a head to tail method. Here's the head, and there is the start of the head, of the tail, I mean. Now, this is our Fy, right? And then the angle is here. So the angle, this 30 degrees is here, right? So this is telling us that we can break this applied force down into two components, which is the X component and the Y component. Why are we using those components? It's simply because there is no question, or there is no way where we calculate the movement, or where we're having the movement of this particular object, which is horizontal, moving diagonal. This object is moving horizontal, right? And then remember, we use the X component to calculate F net of the movement, right? So to calculate the F net of the movement, the net force of the movement. So as we are calculating F net of the movement, it simply means we use Fx when we are focusing on the horizontal forces, because this object is moving horizontal, right? And then we use Fy. Fy, we use it to calculate our friction. So this is a standard way of understanding the components, the use of the components. So now let us break it down so that when you understand what's going on here. So let's break this down. We are going to break this F applied into its components. So breaking it into its components, let me make a free body which is a little bit bigger. We still have our Fg in this case. We still have our normal force, and then we also still have our Fk, right? Then now our components, we're having Fx, which is going to the right. This is our Fx. Oh, why am I using my fingers now? So let me just use a duster. We are having our Fx going to the right, and then we are having our Fy. So this is our Fy, right? So why are we doing this? It's simply because we have to go to the basic principles. We said we use the Y component to calculate the friction. We use the X component to calculate the F net for the movement of an object, right? So let us say our next question now. It says calculate the frictional force. Calculate the frictional force. Now we know the formula of friction, Fk is equal to the coefficient of kinetic multiplied by the normal force, right? Remember, F applied is at an angle now. It is no longer horizontal. Now let us try and understand. Is this object moving up and down? Is it moving vertical? So the answer is no. So if the answer is no, it simply means the F net for the vertical forces, F net for the vertical forces, it must remain as 0. So the F net for the vertical forces, it remains as 0. So now what comprises of those vertical forces? Now the forces are now no longer two, they are now three, which are acting horizontal or vertical, I mean. So remember that we said the forces which are going up, we take them as positive, and the ones which are going down, we take them as negative. So which means this F net for vertical forces, it comprises of the normal force plus the y component, which is our Fy, minus the Fg, is equal to 0 there, right? Therefore, this simply means the normal, if you make the normal the subject, it means Fy is going to be negative when I transpose it to the side, and then Fg is going to be positive when I transpose it to this side. So let us start with the positive one. We said Fg is going to be positive when I transpose, and then Fy is going to be negative when we transpose, right? We remember that Fg can also be expressed as m times g minus the y component. Remember, when we are looking at the y component, we have to consider this angle now. So as we consider this angle, let us look in here. Is the y component adjacent? So when you say adjacent, is it sitting on Fy, or is it opposite of Fy, right? So looking in here, we can see that these two, they are opposites on each other. It's like they are facing each other, they are opposite to one another, right? And then the trig ratio, which is using opposite over hypotenuse, it is the sine. So this simply means this here for Fy, we are going to have F applied multiplied by sine of theta there, right? You can see now that this normal force, it is no longer just m times g, but it is m times g minus the Fa sine theta there, minus the y component. So how does this affect the normal force? So on the normal basis, if there was no the F applied was horizontal as in the previous part. So if it was just horizontal, so it means the normal force, as we still remember, it was just m times g, for which we can do the calculation and say the normal force is 5 multiplied by 9,8, for which I believe we are having 49 9,8, we are having 49 newtons, right? So whenever there is horizontal force applied is applied, or force is applied horizontally, we're having 49 newtons. But now let us check to see what is going to happen if now this is applied at an angle, as in this case. So we're having 5 multiplied by 9,8 minus with 30 sine times sine, the angle is 30 degrees there, right? So if we say 49 minus 30 sine 30 degrees, we are now getting 34 newtons, right? So now the question is, what do you notice as we increase the angle of F applied? It simply means the normal force, it is decreasing. So if the normal force decreases, what does it mean about the friction? The relationship between the friction and normal force, both of them, they are numerators. So it simply means if the normal force decreases, this simply means the frictional force is going to decrease as well, right? So now let us go back to the formula now. We are calculating the friction. Let's get back to our friction. So friction, now we can express it Fk is equal to the kinetic coefficient, uh, open bracket. This is important. Open bracket, Fg minus your Fy, right? The y component. So now let us continue. I will continue on this side. So as I continue on this side, we are now going to say this is Fk is equal to the coefficient, which is 0.17. It is here, it's given to us. Then let's put it under brackets. Fg, we know it's m times g, which is 5 multiplied by 9.8 minus, and then Fy, we remember we said we are using sine because this is this angle and the y component, they are opposites on each other. So this is going to be 30 sine of 30 degrees, right? Sine of an angle. This angle is 30 degrees. Then you close your bracket. And then if we are punching that in the calculator, I believe we shall find 0.17. Okay, 0.17 multiply by 5 times 9.8. I want to make sure that everything is correct. Times minus 30 sine of 30 degrees, close brackets. So we are getting 5.78 newtons. Remember, on the last activity, or on the last scenario, the normal scenario, we were having this frictional force being 8.33. You remember that? Hope you still remember that, right? Okay, so now since we are having this, you can see the relationship between the normal force and the frictional force. You can see the relationship when the force is applied diagonal. What effect does it have on the normal force? And what does the normal force have on the frictional force? The frictional force decreases when you apply the force going diagonally up, right? So now our third question now, let me just leave this in here. Third question is that we are calculating the acceleration now. So let us see, question number 3 calculates acceleration. So calculating the acceleration, one thing you should know is that we are looking at this free body diagram. Now we are focusing only on the horizontal forces. There are two forces which are acting horizontal. Remember that we said we use Fx for F net of the movement, right? So this is the F net of the movement, because when something is accelerating, it means it is moving now. So this F net, remember it comprises of what? The x component of F applied and also the frictional force. So this is going to be Fx. Remember, this side is going to be positive and that side is going to be negative. Where the motion is going, or where the direction of motion is, we take it as positive. So Fx is positive minus your Fk, which is equal to ma. Therefore, Fx, remember now, we are looking at this part. This part, this angle and this side, are they opposite to each other or are they adjacent to each other? So if you are looking in here, this fx, or this angle is sitting on fx, so it means it is adjacent to fx. So this simply means the trig ratio that is using adjacent over hypotenuse is cos. So it means we are having fa cos theta for our fx minus our fk is equal to ma. So now fa, we are having 30 cos, what is the angle? The angle is 30 degrees. So we're having 30 degrees. Oh, of course, we are having a load shedding now, but let us continue there. Regardless, let's just finish this one up. Okay, minus fk. So our fk, we've already calculated our fk here, which is 5,78 is equal to the mass, which is 5 kg A. So punching this in the calculator, we're having 30 cos of 30 degrees, and then minus 5,78. We are having 20,2 is equal to 5a. Remember, to solve for a, we just do the opposite of this 5. What 5 is doing in a, we divide by 5, divide by 5 in both cases. So we're just gonna divide by 5 on this side. We're gonna have 4,04 is equal to a. Therefore our a is equal to 4,04 meters per second squared. In which direction? The answer is positive. This is the direction we took as positive, going to the right. Alright, so now, as you remember from the previous scenario there, which was our first scenario, the value of acceleration, it was 4,33. So it simply means acceleration is also affected the moment you increase the angle here. All right, so hope we'll continue when the load shedding is over. Thank you for listening.